Good afternoon, good morning. My name is Don McDonald. I'm the regional manager for Phoenix Controls here in Canada and part of the US. I've been with Phoenix for 25 years, and today we're going to talk about a case study that we did recently with McLaren Health. McLaren is headquartered in Grand Blanc, Michigan, and is a fully integrated health network committed to quality evidence-based patient care and cost efficiency. McLaren's system includes 15 hospitals in both Michigan and Ohio, and they have cancer centers in those states as well as in Indiana. So a little bit of background. McLaren has this surgery center at their Macomb facility, and it's about 151,000 square foot. They've had 10 operating rooms in there, consistently performing critical operations since about 2005. But they've been having problematic airflow control, air change rate, and pressurization problems. The objective of this project was to provide consistent airflow and room pressurization, analyze what was going on in the space, and then try to maintain the required air changes per hour per the regulatory standards. They had some downtime associated with air control problems, so that we wanted to improve that uptime for those operating spaces, and of course improve patient outcomes by reducing the probability of infection. And also, the staff had some issues with not understanding what was going on in those spaces, and they wanted to have some way of visualizing what it was happening in terms of temperature, flows, pressurization, etc. So as a result of these problems, McLaren worked with our local representative in Michigan to determine what could be done to improve the air system performance and, of course, improve patient outcomes. As we previously heard from James, there is a big difference between VAV boxes and what Phoenix offers. For those of you who didn't have the opportunity to listen to James's Phoenix 101 presentation, I suggest you download that and have a look at it. It's very informative. But in quick summary, a VAV box is basically shown on the left, and these are okay for temperature control in commercial buildings, but are not well suited for precision airflow control and room pressurization. One of the problems with VAV boxes, if we look at exhaust side from a room, for instance, the boxes can tend to get clogged up with lint and dust from bedding and debris. And on the left here, you see the clean VAV box, which will be performing properly. On the right, you see one that's been clogged up after a period of time in use. So that has to be accessed from the room up into the ceiling. The space has to be hoarded off. The box has to be clean, and then it has to be recalibrated. So it's a bit of a maintenance issue, especially when we're trying to maintain a clean environment in a hospital setting. Other issues with the VAV boxes is that we have a limited turn down capability and an accuracy and repeatability issue with VAV boxes. So on the right hand side, you'll see a Venturi valve. And I guess the main difference is that the VAV box measures the flow, measures the velocity, pressure, total pressure, then tries to control that blade damper in the ductwork, okay, to maintain the set point. So either on a change of set point or a change of pressure, we're going to see a fluctuation in that damper trying to maintain the correct flow. With the Venturi valve, it uses a metering principle. So basically, the cone in the throat of the Venturi restricts the airflow, and as that cone is pulled into the Venturi throat, it reduces the airflow, and as it's pushed out, it increases the airflow. So the position of the Venturi valve is what makes the difference in terms of the flow control. And then if there's a static pressure change in the system, that spring and cone assembly will absorb that static pressure to maintain whatever the set point is for the flow. And here we see the quick opening characteristics of a blade damper with some level of controllability. And the inverse relationship here is an equal percentage curve, so that an equal percentage change in position provides an equal percentage change in flow. You can see in the low end of the flow characteristic here, we have to move that valve a lot to get to the correct flow point. So that gives us a lot of accuracy and capability and high turn down capability. So after reviewing this with the folks at McLaren, it was decided to retrofit these 10 operating rooms to provide a more consistent airflow dynamic and pressurization dynamic for these spaces. We look at some of the basic fundamental requirements for ventilation design for operating rooms. ASHRAE 170 2017 has specific guidelines that are have to be adhered to. For instance, the room has to be 0.01 inch positively pressurized with adjoining spaces at all times. So if you've got a sterile corridor or another area, you know, the operating room has to be the most positively pressurized of those areas. 20 air changes when occupied, and that's to ensure that any particles in the room are swept through the space and out away from the patient. But you can reduce that when the room is not being used for a surgery, and we call that the unoccupied mode. No, it's really important that when you switch from occupied to unoccupied, that you maintain that positive pressurization at all times. 4 air changes would be your minimal outside air requirement, and you're typically going to run those rooms at constant volume. So once you're at the 20 air changes or some reduced air changes in the unoccupied mode, you have to stay at that level. During surgery, the temperature ranges from 68 to 75 degrees F. Humidity typically in the 20 to 60% range, and then operation must be capable of responding 24 hours a day, 7 days a week. Your supply diffusers have to have unidirectional downward and an average airflow velocity of about 25 to 35 CFM per square foot. We can see in this picture here, courtesy of SLD Technologies, they have a pretty comprehensive array of diffusers that allows that airflow to come down in a laminar fashion over the patient to maintain a sterile zone. Areas of the diffuser shall extend a minimum of 12 inches beyond the surgical table, and in most cases, typically, you'll see them extended much further than that. The exhaust grills must be at a low level and approximately 8 inches above the floor and as far apart as possible. And that's to get that sweeping motion from the supply diffuser down over the sterile zone of where the patient is and then out to the corners of the room. So if we look at a typical room scenario, and we want this room to be at 20 air change rates per hour, Phoenix Controls will provide a Venturi valve on the supply air flow to that laminar supply air diffuser, and we'll also provide a exhaust air valve on the exhaust side from those low return grills. And basically, we want to set up a situation where we have a positively pressurized space. To do that, we make sure that we have our 3000 CFM or correct number for the 20 air changes per hour. We're going to restrict the exhaust to be less than the total supply. And typically we use about a 10% offset number of the supply air. So we're looking at about a 2700 CFM exhaust and a 3000 CFM supply and a 300 CFM into the corridor, which based on how well sealed that door is, it will generate our required 0.01 inch water column. Now that is a minimum. Most of the time we're shooting for a higher number as an operational pressure. And then this would be our limit for our alarm, which would be monitored by a differential pressure monitor that Phoenix can provide that monitors the pressure between the room and the corridor. Okay. Other variables that we have to make sure that we include for would be our occupancy modes, of course, temperature, humidity, pressure monitoring is required, remote monitoring. We might be using duct temperature sensors on the supply air duct to look at what our discharge air temperature is, and then decontamination. And when we do temperature control in these types of spaces, typically we'll use a reheat coil on the discharge of the air valve, and then that reheat coil control valve is controlled by the Phoenix controller on that supply air valve. And then we do have a space temperature sensor, which can have a display on it, or you may want to display the temperature humidity variables on your pressure monitor or other devices. So that's a typical scenario for occupied air changes. When we want to switch to unoccupied air changes, say we go to 5 unoccupied, right? We basically reduce the supply. The exhaust will track down with the supply until we reach the minimum, but we always maintain this 300 CFM offset. So that offset number is what maintains the pressurization. So even though we're reducing the supply and exhaust flows, this offset stays the same, therefore the pressurization variables should stay the same. So if we look at the airflow turn down, you can see we have about a 4-to-1 supply airflow turn down, but we have about a 6-to-1 exhaust airflow turn down. So it's important to remember that airflow turn down that we've been talking about be maintained, achieved and maintained during this process. Now, if we go and look at what was happening at McLaren, this was their air change rate variables for the Macomb Surgery Center, the various operating rooms. So if you look at the top here, that was OR1 air changes, this blue color here, OR2, OR3, etc. And you can see their target was this orange line, or about 20 air changes per hour. And in reality, they were all over the map. You can see that they're probably on average around 30 air changes for most of these rooms, and somewhere around 22 to 24 air changes for these rooms. So this is a big problem for them. Swings in pressurization come along with that, depending on how well sealed the room is, etc. So after we analyzed what was happening in the space, what the VAV boxes were doing, again, recommended Phoenix provide Venturi air valves. And here we are with the result of the Phoenix installation in terms of air changes per hour. And you can see how stable this is for all the operating rooms. Very stable right across the time variable. And this is with, again, as I said, the Venturi valves. So basically night and day compared to what was going on prior to that. Now, I did mention earlier that one of the things that McLaren wanted to understand was the key performance indicators like temperature, pressure, humidity, etc. They had pressure monitors used in the space, but they also wanted to be able to look at a combination of variables out in the corridor before you go into the operating room. And if we look a little closer, you can see that they're monitoring some critical parameters here: their temperature, their humidity, the pressurization of the room. You see the required was 0.01, but we're getting up to almost 0.02 inches of water column. Alarms, they wanted a quick and independent display of alarm conditions. So this area of the screen will turn red if there's an alarm. It will indicate what the alarm is. Here's some more variables that they wanted to show, and then they can change the occupancy mode in this space by touching this part of the screen and then selecting from several variables for occupied, unoccupied, or standby mode for these rooms. So they were able to visualize and see what was going on in that space. Interesting comments from some of the folks at McLaren. So the director of the Macomb facility said they've noticed the consistency of the air change rate and have been able to see the current temperature. They really didn't have a good understanding of those regulatory compliance items visually before, and now they can see it. It's all there for them. So they understand each of the 10 ORs has the same setup. So if they're looking at OR1 or OR5, it doesn't matter. They see the same information formatted outside the OR and inside the OR. So they're confident that their surgical suites are cleaner and safer and for better patient healing and outcomes. So another comment from the manager of engineering, energy engineering and integration services: we already see a measurable difference in the ability to maintain the target air change rates as the air no longer has to condition 16,000 CFM plus. So that's what they figure that they were wasting. We've also seen a reduction in the air energy supply, and in return, it's literally day and night for that building. So, you might not see much of an impact if you got 1 or 2 hours, but certainly with 10, it makes one heck of a difference. And in summary, the surgery center stands to save approximately $250,000 a year in operational cost. And if you listen to James's presentation, he went into some more detail on the cost per air change rate, which I think was about $4,000 per 2 air changes. And so with that ability to go from 20 to 10 air change rates, which is their elected number to use, when not in surgery mode, the airflow decreases by half for significant energy savings. Company called Resolute Building Intelligence does remote monitoring of McLaren's facilities, and they're looking at other ways to save energy in some of their other facilities, including additional retrofits using the Phoenix Controls approach. There you go. Thank you very much for your time, and I hope this has been educational. And Phoenix does have a case study document for the McLaren Macomb operating room retrofit. If you'd like a copy, please just give Dave a call or email.